Good morning. It's a fairly lengthy title. I think we can trim it down a bit to Source to Sink of the Eastern Mediterranean, which coincidentally is the title of a study we finished earlier this year. When we're talking about source, we're talking about sediment sources and their transport pathways to ultimately the depositional areas, the sink, not the kitchen sink, as one gentleman I met with thought that referred to. And we are concentrating on the Eastern Mediterranean. If you're not familiar with Getech, we're probably most well known for our gravity and magnetic data holdings. We've got the largest library of that kind of data globally. We were able to talk about all sorts of things to do with the geometries of sedimentary basins, but we've now also got a number of geoscientists who can talk about various aspects of what's actually going on within sedimentary basins. And particularly with the techniques we're using, it's very much kind of frontier-focused areas, as has already been alluded to. So we'll be looking at the Eastern Mediterranean. It's probably worth just having a look at what we know and why we might wish to do this kind of work. So here we are, sort of offshore Israel. And what we want to do is understand what's going on with the discoveries that have already been made, and then see if we can extrapolate that north. Obviously, there's an ongoing license round in Lebanon. Okay, there's some delays at the moment. We'll see ultimately what happens with that. But there's still opportunities to explore there. So first of all, we can notice that there's two clusters. So we've got these Paleocene biogenic gas reservoirs down here, Gaza Marine and the Pinnacles and Noah B fields. And then the fields that people have really got interested in, the lower Miocene, again, mostly biogenic gas, although there are hints of deeper liquids. And the reds are obviously the gas fields, the yellows are prospects, which have been in the public domain. And you can immediately see two trends. There's a northeast-southwest trend, and if you look particularly at some of the detailed field shapes, and particularly with all the prospects on, you can see there's a southeast-northwest trend as well. Sorry. Oh. So I skipped ahead one slide there. It's very sensitive, this. So you can see with the gravity data in the background there, that there's the kind of structural control on that northeast-southwest trend. So really what we've got to do is start to think about what might be causing the other trend. You can see, oh, sorry. It's very sensitive. Right. And you can see that structural control here on this spectrum seismic line that was presented at the Light Conference by Neil Hodgson back in 2012. You can see the top lower Miocene, top middle Miocene. This is the Messinian salt in the region. It's worth pointing out, whilst I've got this slide here, the salt is not the regional seal for these reservoirs. There are other sediments in here. And really we need to look at why you're getting an onset of reservoir development and what's turned that off ultimately. So coming back to this slide, we want to look at this northwest-southeast trend. What might that be? There's an excellent paper published by the Israeli Geological Survey, the Gardouche et al. 2008 paper. If you're looking in this region, I'd recommend having a read of that. What we're looking at here on this map is the top lower Miocene surface and various channels that have been mapped out. And here for the Ashdod channel, you can see a couple of sections. This lower section is somewhere up here. The orange horizon is the base Oligocene, and the kind of cyan colour there is the top lower Miocene, so that relates to that surface there. And you can see the thickening out into the deeper waters. So this top seismic profile comes from somewhere out here, and you can see these parallel reflectors kind of stacked up, so probably submarine fans there. And we can have a look at those channels against our gravity and against the field shapes, and you can see that probably that northwest-southeast trend is down to depositional features. It may well be that is sort of retained in here, so it follows that channel down. They're fairly long-lived channels. They've also been mapped here for the top Mycenaean, so you can see how they probably relate to the Pleistocene fields down in the south. But there's a bit of a problem. It's all very well imagining that you're sort of bringing sediments off the shelf and into the deeper water in that direction. But if you look at the geology of the onshore, particularly of everything sort of west of the Dead Sea Fault, it's mostly carbonates. The only real clastic sources, and we know that we're dealing with coarse sands out here in the lower Miocene, but the only clastics really come from the cores of Syrian arc features. And I'll just highlight those on this geological map in this purple colour. And you can see how little there is really potential sediment for distribution out into the deeper water. And there's a huge amount of clastic sediments out there. So this really comes to the big question when you're exploring in this region. What's the source of these lower Miocene sediments? And if you can understand that, then you're going to de-risk your exploration for further in the north into Lebanon. I'm going to try and answer it by looking at the tectonics and hinterland evolution, and also the climate and ocean currents as well. So if it's not this immediate area, what are the other contenders in the region? Well, the Nile is the obvious one, and a lot of people have alluded to that in the past. But there are other options, and we're going to look at some of those today. I'll explain a bit more about what the Red Sea Rift is in a moment. Sinai is obviously a possibility. There's the greater Levant margin, so what's going on to the east of the Dead Sea Fault. We can look up in western Syria. That's the upper portion of the Euphrates. You can imagine how that might have drained sort of down into the northern area, through western Syria, southern Turkey, and you know, we'll have a look at Cyprus. In fact, we can have a look at that now. This is actually a subduction zone, and basically it's a sediment trapping mechanism. It's very unlikely that you can get sediments from this region sort of down into the main part of the Levant, which is not all bad news actually, because there's a lot of volcanics there, and that's going to have an impact on reservoir quality. So before we look at those contenders in too much detail, I'm just going to talk through some of the methodologies that we're using. I'll talk a bit about the data sets and processing, because it will be obvious that there is processing involved when we look at this region. What we do is we start off with topography, digital elevation models, and from that we can automatically generate stream networks and drainage basins. And when we talk about these digital elevation models, what we're talking about is the Shuttle Radar Topography Mission, SRTM, and there's two resolutions of that, the SRTM30 and the SRTM3, and you can see the difference in detail there. There's about 90-meter resolution in the SRTM3. Obviously there's more detail on this, but there's more processing time required as well. So what we've done is we've looked at the SRTM3 for the immediate margin of the Levant Basin, and then when we're looking at the rest of the Nile, we're looking at the SRTM30. Now we do have to do a bit of processing, and that's really to fill voids and sinks. The voids are areas where there's no data, and the sinks are natural features like lakes and internally draining basins, but also sometimes data artifacts, which you get especially in areas of steep topography. Basically, if we want to do the kind of automated drainage analysis that we run, we need to sort of fill these sinks and voids, basically so that they're a level surface. And what that looks like on the drainage maps are these generally sort of north-south lines, but also east-west lines as well. And we need to do this in order to do some of the other stuff that I'm going to show you in a moment. And you can see examples of these. Obviously, the Dead Sea, we know that's an internally draining basin, Sea of Galilee, the wadis down here. And yeah, we've done the processing for this whole region, and we're able to then generate these networks. But you can already start to just, even looking at this image, pick out some of the patterns. I mean, there's a classic example of radial drainage here on the East Safa volcanic cone. This sort of line in here, which continues through, that's obviously quite an old drainage divide there. So this part of the drainage system has probably sort of drained up in this direction. It's the emplacement of that volcanic cone that's provided more energy, and there's been sort of headward erosion up this system and sort of breached that drainage divide there. So you know, you can already start to pick out some of the changes that are evidenced in the modern day drainage network. And it's really these drainage patterns that we're looking for. I mean, this is the kind of classic example of drainage patterns that you expect to see, but there's all sorts of different drainage patterns, all influenced either by tectonics or geology. But there's a further influence, and it's very well summarized by the Summerfield in his 1991 paper, that drainage systems tend to have a heritage rather than an origin. It's very rare that you get a tectonic event that will so completely wipe the slate clean with drainage patterns that they don't somehow influence the evolution or the next stage in their evolution of drainage patterns. And we'll look at sort of two end members of how that works. So a picture here of the Potomac and Shenandoah River. Washington, D.C. is off in the distance there somewhere. And this is an example of antecedent drainage. So what's happened here is that the river has been eroding down through the geology, kind of stripping it off, has eventually eroded through an unconformity. You've got this, I think it's Carboniferous age lithologies and this syncline. And apart from this kind of little blip around one of the limbs of that syncline, the river is pretty much eroded straight through all of the features of the geology at this level. So this is an example where the underlying geology has had little effect on the drainage patterns. An example at the kind of opposite end of the spectrum, this is from the southern Congo drainage basin, where you've had tilting from the south. That gives extra energy to the drainage systems, and you get this, again, textbook example of parallel drainage as the drainage systems incised back into that uplift. More often, though, we're dealing with somewhere between those two end members. Barred confluences is a good place to start. So if we have a look at this image, it's obviously based on the SRTM 30. This is from the Nyong River in Cameroon, West Africa. And I've just put on these blue arrows to kind of show the tributaries as they join the main drainage system. And you might imagine that that's how the main drainage system goes. But of course, if you follow this arrow out, you suddenly realize you're actually going upstream. And in fact, this is all upstream as well. That's in fact the main drainage trend as it stands. When we're looking at the tributaries here, you'll notice that although they're kind of counterintuitive in terms of the trend, it's a past drainage system that's been reflected there. Just a little cartoon to illustrate what we're looking at here. So at time zero, you've got the drainage flowing from the right to the left. There's then a reversal in flow, and then you get erosion on the downstream side of these tributaries, and you get these little barbs, these little hooks at the confluences. And that's what you can see in this point here. So basically, the drainage direction has reversed over time within this river system. Whoops. And you can see where we've marked the BCs here on this map of the Nile, that there are lots of these barbed confluences in the Nile system. So there is evidence of reversals of flow. There's also other sort of more sort of geological features as well, which suggest that there's been reversal of flow. So there's been several stages of reorganization. We'll come back to this map in a moment. Just want to look at one other feature you can see, and just to explain, I've got an example here from Southeast Asia. This is the Red River Fault, and a river in there flowing down to the Songhong Basin. This is the Pearl River flowing out towards sort of Hong Kong, and this is the Yangtze. And we'll just focus in on this small area, particularly this sort of quite sharp angle in the drainage system. And this is what we call an elbow of capture. And you can also see in the topography this wind gap here. So what's happened is that the Yangtze has been eroding into the headland and has captured the upper portions of another drainage system. There's been a drop in base level, there's been erosion, and this sort of canyon develops in this particular case and leaves this kind of, not uplifted, but higher exposed wind gap, this dry river valley. So here we can start to talk about what the paleo drainage trends might have looked like. So at one point, all these lithologies up here were being eroded, transported down into the Red River and out to the Songhong Basin. You could see that kind of right angle bend in the original image on the Pearl River. So at some point, this is eroded backwards. It's captured this drainage system here, and then subsequently the Yangtze is eroded back and captured all this area as well, which is all very nice, but how does this help us with the exploration? Well, understanding what lithologies are being eroded and where they're being transported to and when is obviously going to have a major impact on your understanding of the petroleum systems. There's 18 kilometres of sediment in the Songhong Basin. It's got to have come from somewhere, and most likely it's come from here. It's not sort of erosion down here with the modern river. And again, we can see lots of these sort of right angle bends, these elbows of capture in the Nile. There's a particularly enigmatic curve here, sort of corner. The white line shows the edge of the Eocene limestone. So it's obviously been a major control on the drainage evolution, a bit of a barrier really. There are hints that basically during the Mycenaean, when you get base level drop in the Mediterranean, that's when this is, the escarpment has been breached. And effectively what was happening is that the Red Sea hills were basically sort of coming down round the long way, as it were, or across here. So there's been several phases of reorganization really within the Nile. Various different points at which it's exited onto the North African coast. There's lots of other things we can do in order to analyse drainage systems. So this is some hypsometry. So we're plotting here the basin area effectively against elevation. And if you've got a nice mature drainage system, this is what you expect to see. So an example from the Tana River in Kenya. There's a bit of a blip there, so it's worth looking at that area to see what's caused that. But this is that river from Cameroon we were looking at earlier, the kind of textbook example of the barbed confluences. And this is that upper portion that we were looking at. You can see it's quite a mature sort of shape of drainage basin, apart from this big nick point. And effectively what's happened is that there's been a river capture event, and that's what's caused that reversal of flow in that river. So again, this has been done for all the drainage systems in the Eastern Mediterranean. We can look at river long profiles. So we're plotting distance from outfall against elevation for every node within the drainage system. Again, what you're looking for are these kind of nick points, which are indicative of either uplift or river capture. So this example from southern Africa of the Orange River, where you've had sort of erosion through the rift shoulder, capture of this sub-basin, and then that's eroded back and ultimately captured the whole of that Orange River system. So again, the questions to ask here is, when did this happen? Why did that happen? And where was this draining to before? So the cutoff plane it goes both ways, really. We can see that incision if we look at some of the topographic derivatives that we do. So the low-pass filter is a 50 kilometre rolling average. And if we take that away from the modern-day landscape, then we get this high-pass filter. And you can see with these blues that sort of incision back into the Orange River. So you can see where there's been that sort of high-frequency changes in the landscape, which are indicative of changes to the drainage systems. And it's always useful to just have a look at some topographic profile analysis. So an example here from the Amazon. You can tend to pick out the paleo surfaces. You can get indications of the amount of sediment that's ultimately been eroded. And if you tie that together with the rest of the story, then you've got some idea as to the sort of volumes of sediment you would expect to see ultimately when you're looking at your seismic data in the offshore. So we'll come back to our contenders now for the Eastern Mediterranean, now that we've had a look at some of the methodologies that we've used, just in terms of looking at the paleo drainage. I mentioned the Red Sea Rift earlier. Oops. So as you see from the next slide, we're going to come on to the paleogeographies, but this is just an example from the Oligocene. And the hypothesis here is that you've got this fairly sort of long rift system. You've got the possibility to erode both off the Red Sea hills and the Arabian Shield into that rift system. And there's a general trend away from the Afar High towards the Levant Basin. Of course, what generally tends to happen in rift systems is lots of segmentation and various ways of accommodating stress. So what you tend to find is that there'll be lots of little sort of lake systems in here, each of those acting as a sediment trap. So whilst it's worthy of consideration, and we need to look to see if there's evidence, although probably, as it's now under the Red Sea, a little difficult, but some evidence of where those lakes may have been, and we can sort of look to see if that's a reasonable hypothesis for a sediment source into the Levant. Whilst we've got the map up, we'll have a look at the Sinai as well. There's only really one major drainage system there now, but of course, you know, in the lower Miocene, this is before the Red Sea fault has activated. If you imagine sort of this whole area of the Arabian Shield has to come down relative to the Sinai Peninsula, and we've got these, you know, fairly big drainage systems. Okay, there's some fairly long-lived sediment traps in here and in here, but ultimately they're going to have been flowing sort of up through the Sinai and certainly sort of lower parts of Israel there. So in terms of the Sinai, I mean, you know, again, you've got that limiting factor of the amount of lower Cretaceous or older sediments as being a source for clastic sediments. And then you also have to look at these kind of long-lived sediment trapping mechanisms as to reasons why these may not be the sediment sources. So we're just going to have a look at the paleogeographic evolution of the Eastern Mediterranean. We've been working over the last few years on a series of global paleogeographies. We're now working on the Permo-Triassic, having done the Jurassic, Cretaceous and Cenozoic with time slices for each stratigraphic stage. Before we do, though, I'll just sort of explain a little bit more about the sort of methodology that we use in our paleogeographic mapping. If we imagine this as the modern day landscape here, we can think of that in terms of base level, so this red surface here. So it's a theoretical surface at which there's no net erosion or deposition. If you're below base level, then you're getting deposition, and what you can map out are the gross depositional environments to give you a bit more sort of control and understanding of that. If you're above base level, then you're getting erosion. And we can map that out as well by mapping out what we call tectonophysiographic terrains. So these might be areas of, say, continent-continent collision. And we also need to understand their age relative to the time slice that we're dealing with. Obviously, this is the modern day. But if you imagine something like the Caledonides and the Himalayas, tectonically very similar regions, the only difference is the relative age. So if we can map these out historically, and we have a plate model which allows us to rotate data, and we can use this as an analog, then what we can do is we can map out landscapes based on these paleogeographic maps. So we're effectively mapping out landscape from first principles. So this is an example from the Paleocene, and what I'm going to do is sort of run through each of the time slices towards the modern day with a couple of comments along the way. What we've done is centered this on sort of Beirut and Tel Aviv. So you'll see those stay in the middle of the slide, and you'll see the lats and longs around the side change. Ultimately, what's happening, of course, is that the African plate is moving northward and colliding with Eurasia. It's worth noting as well that this is the coastline down here, and we'll see as we move forward that it slowly sort of progrades to the north as well. You can see the country boundaries in the background, so it's not, I'm not showing the plate boundaries, but obviously the country boundaries rotated back on the plate model are fairly fixed relative to the plates. So this is a change in the actual coastline as it progrades to the north. And as we get into the Eocene, you're starting to get much more sort of uplift in the region of the Afar Dome. And then we get into the Oligocene. This is when we get that first big pulse of sedimentation into the Levant margin. And it's all this uplift on the Arabian Shield and in the Red Sea hills. It's also when we get the first, or the oldest sort of reorganization event that we can see in the Nile, where what were internally draining basins down here in sort of Darfur area are actually sort of captured and join the main sort of Nile system, although it's still not as extensive as it is today. And this is where we see that idea of the Red Sea Rift as well as a potential sediment source area. And then we move through the Oligocene into the Miocene, and this is now where we're getting reservoir development in the Levant basin. And I mentioned that we have these fairly long-lived sediment traps in the sort of hinterland of the Levant margin. This, you can see this in terms of the geological evidence. There's lacustrine facies in there. So they are long-lived features, and they need to be accounted for in the story. So all this while, we're getting reservoir deposition in the Levant. And it's worth noticing, just before we sort of move over into the period where we're not getting reservoir development, the sort of last sort of chance for reservoir development here. So, we certainly have a Nile system coming out here. You're getting a lot of erosion on the Red Sea hills. You've still got those long-lived sediment traps. And what we're going to see now is movement on the Dead Sea Fault. And I think something worth noting is that this seaway, which is actually open to what's now the Indian Ocean, is still present at this time. So when you get movement on the Dead Sea Fault, that closes off for the final time. And this, of course, is another time at which you're developing the Dead Sea and the Sea of Galilee. Again, major sediment traps. Now impossible to get anything across those now. And then we move through into the Mycenian. We're mapping high stand on our maps. So obviously, at this point, the Mediterranean is completely sealed off, and sea levels sort of dropping and dropping as you're getting evaporation and development of salt in the region. So none of these actually sort of go out to open ocean, as it were. And then we move into the Pliocene, into the last glacial maximum as well. Okay. So one thing we've been doing recently is using the bathymetries that we've produced from our global paleogeographies. We've been passing those on to Imperial College here in London, and they've been running their tide models on those bathymetries. So it's fairly new work. It's not included in the original study, but I think it's worth sharing with you a couple of images. So this is whilst you've still got reservoir development in the Levant basin, and you can see these tidal bed shear stresses. The colours relate to the grain sizes that can be deposited under these circumstances. Obviously, that's predicated by an availability of those grain sizes to be sort of moved around and deposited. And as we move into the Cereavalian, that's when you cease to get that seaway and you stop getting any kind of shear stresses in here, or any major shear stresses anyway. So there is a sort of redistribution of sediments using the tides. There's also the opportunity as well for longshore drift as well, and is there the possibility for tropical storms and sort of movement of or sort of wave action as well to redistribute sediments. And that's important to consider if you think that the Nile is potentially the source. It's coming in here. If you can move it round onto this margin, you can keep on feeding those channels and get sediments into the deep offshore. And that's something you see on the west coast of America. There are fairly major channels there that you can see. You can see them if you just look on Google Maps, actually. And the feeding rivers into them are fairly ephemeral affairs, but there's constant sort of sediment feeding down these canyons. One of the local oceanographic institutes have some sediment traps in them, and they can pick out where those sediments are coming from. And effectively, you're getting erosion sort of further down the coast, longshore drift, and then the sediments find their way into these channels again and again and again. And it's this constant sort of movement of sediment up the coast and then down into the offshore, reusing channels that are already there. So that's the kind of model for bringing sediments in from the Nile, moving them, potentially sorting them to some degree, and then feeding them off. Of course, it's probably easier to bring in, or easier in terms of the model, to bring in sediment sort of straight across the Levant, or the greater Levant margin. But as we've seen, there's a lot of carbonates up here, and the general sort of trend for drainage would actually be up to the kind of northwest as well. But again, you're maybe sort of bringing it down and then sort of reworking it back round, and then bringing it up into the Levant margin then. Just talk briefly on paleoclimate. It does have a big effect on what we're looking at here. We can think of it in terms of many scales, but I'm just going to look at the kind of global influence here. Middle Miocene, you're getting some fairly fundamental events which start to affect climate. You're getting uplift of kind of eastern coast of America here and the Tibetan Plateau. Basically, there's a change in the jet stream at this time. And ultimately, this leads to a cooling and a drying over Europe. As you move from the Aquitanian, we've got actually fairly lush subtropical forests there. You're actually starting to get development of deserts in North Africa at this time. And obviously that trend continues up until the modern day. There's also a change sort of down here where Panama sort of blocks off what's until that point a kind of salinity-driven current which sort of goes around the equator at this time. So with that blocked off as well, then you're starting to get other climatic effects and changes to the climate, all ultimately leading to the sort of ice house and glaciation that we've seen. And what we've done is we've mapped out the biomes for kind of key time slices to try and sort of see the evidence of climate change. Of course, we're also using our global bathymetries and landscapes. We're passing those through the Hadley Centre climate model, which is the same model used by the IPCC. And we're mapping out paleoclimate for all the time slices that we're currently working on. This is more sort of, rather than sort of forward modelling of climate response, this is us actually mapping out evidence for climate for these various time slices. And things like the amount of rainfall you're going to get, that's obviously going to influence the energy within your drainage systems, the vegetation that's there, that has both a trapping effect, but also you've got to think in terms of potential source rocks as well, and what the carbon factory might look like in the hinterland. So just a few conclusions, just to kind of pick out some of the main points from what we've been talking about. So this northwest-southeast depositional trend is fairly well supported by both the literature and our models. The immediate Levant margin is probably not the source of lower Miocene sediment, so I think it's almost certainly not. There just isn't enough clastic material there in order to account for the amount of clastic material that's in the offshore. So we have to be looking elsewhere. Probably the Nile and or the Arabian Shield, although there are problems with that. You've got to consider all the phases of the evolution of the Nile. It is quite a complicated affair. And there are also these long-lived sediment trapping mechanisms on the kind of greater Levant margin to the east of the Dead Sea Fault. So you've got to bring all these different aspects together really to understand what's going on in the hinterland and where these sediments may have come from. I'd urge you really, wherever you're exploring, to consider the regional picture. In this particular case, we want to understand what actually began reservoir development. We've seen that uplift of the Arabian Shield and the Red Sea hills. That's probably the impetus for the beginning of Oligocene clastic sedimentation into the Levant margin, into the Levant basin, sorry. But one thing which I think is quite overlooked in this particular area is what's actually stopped the reservoir development. Is it because as you start to get the Dead Sea fault moving, that becomes the kind of ultimate sediment trap, which stops the Levant margin being the sediment source, or is it the effect on ocean currents and tidal currents, which stop you removing the deposition from the Nile sort of further round onto that margin? And I'd also urge you to consider as well climatic effects as well, and how that is going to influence the petroleum systems wherever you're looking in the world, really. And just before I sort of finish up, I'd just like to quickly mention, if I may, that we're considering a new report looking at hydrocarbon maturation and migration histories in northern Arabia. So it's potentially of interest to some of you here. It's been co-authored with Saad Yassim, who's a former chief geologist with the Iraqi Geological Survey. And it's basically a 3D basin modelling project, looking at hydrocarbon expulsion, migration, breaching and remigration or loss in the northern Arabian plate, and really dealing with Kurdistan, southeast Turkey and Syria. So if you've got any questions on that, then I'd be more than happy to speak to you during the coffee breaks. So I'll finish up there. If you've got any questions, I'll be more than happy to give it a go. Thank you.
I think we have time for maybe, you got the microphone, time for one question, if anybody has one. Okay, thank you for that. No, one here, right. Sorry, Bob.
Bob Waterhouse, RG Petroleum. It seems from what you're saying that the deposition of the reservoir rock itself is relatively young in terms of in geological time. Do you see the actual source rock, the actual carbon material, as being deposited as part of the processes that you've been describing there, or would you see the actual deposition of the carbon material as potentially being earlier than that in that particular region?
Well, it's all biogenic gas that's been discovered now. There are rumours that there are liquids sort of deeper in the succession. There's no indication at this time as to what the source rock actually is. Some of the areas are I mean, you know, it's quite deep areas now. Whether it's deep enough to have kind of switched off biogenic gas production is a question. The main control really is going to be the amount of nutrients that's available to the bugs that are generating the gases. Whether that's sort of pre-reservoir, post-reservoir sort of carbon that's being sort of eaten by the bugs and generating the gases, there's no information out there as of yet. But what's clear is that the climate change has probably had an impact on that. So if I was going to, hazard a guess, I'd probably go for something pre-reservoir, just purely based on the climatic effects and the ability really to generate more carbon to bring into the system.
Okay, thank you, Dirk. Our next